So when you think about it for a little bit, you'll see there's really only two possibilities. If we're trying to find the shortest path from I to j that is allowed to use k and any of the nodes with numbers smaller than k, there's two possibilities. It may be that we don't need to use k at all for the smallest path. We just follow a path from I to j, only using nodes who have values less than k. Or we go and we visit k, and then we go from k to j. But in visiting k, we don't ever need to visit k on the way to k. That wouldn't be a very good path. So the shortest path from I to k, only using nodes that are less than k, then we follow another path now from k to j, only using nodes whose numbers are less than k. Those are the only things that can happen. We don't want to visit k twice, and we're not allowed to use any nodes that are greater than k. So those are the two possibilities. And whichever one of these two things is shortest, right, the shortest path from I to k followed by the shortest path from k to j, or the shortest path from I to j, whichever of those two things is shortest, is the shortest path from I to j, possibly using k and things less than k. So we can just write that in a straightforward way by taking advantage of the fact that someone has given us dk. Not tooth decay, but matrix decay, right? So the shortest value, the length of the shortest path from I to k, not using only nodes less than k, we have that already. Someone gave it to us very helpfully. So all we need to do is compare the distance of I to j not using k and the distance from I to k not using k and k to j not using k. It's weird, but it's the right thing to do. So we can take advantage of this insight to actually create an efficient algorithm. So we can initialize d0, so this is the length of the shortest path from I to j using nodes only numbered less than 0, which is to say no intermediate nodes. Well, that's just the direct cost of going from I to j. So we could just fill in from the cost in our graph, we can fill in this matrix. And once we have d sub 0 initialized, we can run k from 0 to n minus 1, and for each pair of I and j, we take dk plus 1 to be the smaller of dkij and dkik, dkij added together, just as I was just describing before. When this is all over, when this loop is done, we have dn. Well, but dnij is the length of the shortest path from I to j, only hopping on nodes that are numbered less than n, but that's all the nodes. All the nodes are numbered less than n. They're all numbered from 0 to n minus 1. So this is the length of the shortest path from I to j, unrestricted, full stop. So that's pretty cool. And if you think about what's going on here, this initialization step runs over all pairs of nodes, so that's n squared. This loop runs over all pairs of nodes n squared, but it does this for each value from 0 to n minus 1. So altogether, we're talking about n times n squared, or n cubed. This is better than the n cubed log n we get by applying repeated Dijkstra to a dense graph. So for a dense graph, you're better off using Floyd Warshall n cubed instead of the n cubed log n. Now, log n is often not that huge a number, so your mileage may vary. You should actually try the overhead. But boy, it's hard to imagine having less overhead than this. It very straightforwardly runs through the n cubed possibilities. And in fact, if you do this carefully, you don't need to keep a separate D matrix for each of these cases. You can actually do these updates completely in place. So the storage is pretty low too.